quantum circuit, you need an operator to work with. So what was operators of zeros. With this, all these zeros and ones, they are in matrices. So this is how they are being called. This is the process. We have this for one, this is another one, this is another row. So this is the matrix by row. 1, 2, 3, 4. I think this should be 4 by 4. Yes, 4 by 4 matrices. So this is 2 dimension output. So these are the operators when we run it. This is what we get, and so this is the, so you can able to see that it's working because the data and okay. So that's what I say. It's in 4 by 4 matrices. So this is the output 4 by 4 matrices. So this is how our data is for P operator, which is a poly operator. So looking at the quantum operators, these are in different sections. We are going to be looking at different operators that are available in quantum theory. There are we have single quantum operator gate. We have multiple quantum operator gate. We have measurement. We have reset. We have conditional, and we have state initialization of operators that we have. So these are the six ones that is common, and we also show you in a different simulation. So we can simulate it in this different perspective of QAS simulators. We have state simulators. Actually, looking at quantum qubit state, we have a single state. This actually we talk of the single state of quantum computing, which we have an alpha and our beta, which is equal to what? Equal to 1 when we have what? When we are representing it in qubit state. So this is what we are going to get. In single state, the single state gates are available in such ways. Where we have U gates, these are the gates we have. We have the C gate, we have the poly gate, we have the amplifier gate, and we have the P gate, and we have the U gate. So we are going to be talking of this single gate that we have. And the U gate is being called when you have a key is equal to what? Cubic register open bracket 1. Now we are writing a code of it for us to be able to show it. Now we have a QC is equal to qubit socket bracket of Q. We are calling our register qubit register, which is in 1 qubit. So we have QC dot U of pi divided by 2, comma pi divided by 4, comma pi divided by 8. So we call our qubit register, and this is the output it's going to give us. This is how it's going to be. You can call it in any of your sockets. Okay, you have different sockets where you have your measurement, you have your S gate, you have different gates on top. You can add your U gate for your gate to for your qubit to able to rotate around the bias of it. The angle is in 3 dimensions of rotation. While we have the lambda, we have the theta, and we have the phi. So now if you want to simulate it, this is what is going to give it to us in an array, which is going to be in math. This is what's going to give to us in array. So I just want us to have the tip of all the gates that we have in quantum. No, the next one is before we go to the next one, we are under part of the qubit gate that we have. We are under the 2 qubit gate, and the first one we talk of is the U gate. The next one now is the P gate, and the P gate is the phase gate in quantum computing. In quantum computing, it's called a phase gate, which is representing the matrix P. So the P is what? The lambda is equal to what? U open bracket 0, 0, lambda gate as the matrix form, which is useful as it is allowed to use to apply to a quantum phase. And this is the matrix form of it, where we have 0, 1, 0, and exponential I lambda. How the math is, and in the form of the code for us to have it. So we have QC is equal to what? Qubit, and you know that our Q, this Q is 1 qubit, is Q register is 1 qubit. So in that aspect, you have QC is equal to quantum circuit open bracket Q. Actually, you can write 1 here. You don't want to write Q, but it's another area. We'll be talking of what to put in our how many qubits we want, how many registers we want it to have. So we have Q is equal to P open bracket pi over 2 comma Q, where the Q is representing what? The register that we have, and Q dot draw. Now we are drawing it. It's going to give us our P gate, our phase gate. So that's that, and we run it in back end of it, which will give us the matrices of 1.0.j, which is in .j, 0.0.j as well. So identifier gate. This is another gate in quantum computing, and which is under single qubit. Where we have identifier gate. The identifier gate is equal to ID is equal to P open bracket 0. Here we have QC is equal to quantum socket Q, and under this quantum socket Q we have Q dot I G open bracket Q and QC dot draw, and let's run and see what it's going to give us. So this one is going to be on one of the cycles that we have. If it's just only single cycle that we have, you have this is a Q on K2, one of the sockets that we have, and we are having only single qubit. We have I, so an expire, and also we have the polling gate. Polling gate is to flip one gate to another. So this flip of of gate X is defined as what? When you have 0 in your matrix 0 1 1 0 1 is equal to u open bracket pi comma 0 comma pi. So in this aspect we have what? We have the X flipping of gate. You are flipping your X gate. You are flipping your S gate from 0 to 1 or from 1. So that's when you are flipping your what? Your gate. That's poly gate. And poly gate we still have Y own. And let me run this. This when you are running, this is what you are going to get when you are drawing it or when you want to structure it. This is what is going to come out. You have what? You have a QC is equal to what? Quantum socket 1, quantum socket 2, and we have QC dot X. You call the X gate that you are talking about, but that's a bit flip. You are flipping. It's just like you are flipping from 0 to 1, or you want to flip from 1 to 0. On a norm, a quantum socket is on a neutral level of 0. So I want to flip it to 1. I use what? I use the S gate. So let me see how what is going to be in what? In back end, which is 0.0.j. So that's moving to the Y bit to flip or the Y bit and face flipping gate. So the Y gate is defined as 0 in matrices form. Mark is 0 minus I open and I 0 is equal to U open bracket pi comma pi divided by 2 comma pi divided by 2. So in this aspect as well, you will have this is the same code whereby you just change your what? Your gate from X to Y, where you have Q dot Y. You flip it, you change it to Y. Yeah, you're going to give us what? Y gate. And likewise, you look at the back end as well. Also, we have the Z phase flipping gate as well, where they have the matrix of 1 0 1 and 0 minus 1, which is P open bracket pi. And coming here, you change as well. You change your Y. You change your Y to what? To Z. If I come here, I change this one to what? To F. It's going to what? Give me the former one. And if I remove it and I change it to Z, it's going to give me what? It's going to give me the Z flipping gate. Let me run it. So you can see now. Let's run the back end as well. So that's, and we are looking at the other gate which we call Adamon gate. This Adamon gate we have is being used in also flipping as well. Where we have H is equal to 1 over root 2, 1 over matrices of 1 1 and 1 comma 1. This is 2 by 2 matrix, or equal to U, which is open bracket lambda. Sorry, open bracket pi comma pi divided by 2 comma pi divided by 2 as well. Let's run. It's still the same code. Where you have your what? You have your quantum. You define your quantum socket, which is holding what? 1 qubit. And here you have what? QC. You are calling your QC, which is QC.H, which is standing for what? Adamon gate. So from there you open a bracket of what? Q, which is just what? 1 quantum register of that, and you draw Q.draw and you run it. So it's going to give you this. Likewise, running the back end as well is going to give us the matrices format of the back end. Also, we have the S. Okay, so that's the single qubit gate. This is the single qubit gate we are talking about, and we are still going to move the other gate. We have a lot of gates in quantum. So looking at the S or Z phase gate, whereby you add your S to your gate, and this is the matrices format. And when you add it, it's going to give us this. If you are doing the calculation, this is the matrices you will use in addition of what? Maybe of 1 qubit, which is going to be 0 and 1. If you multiply it, it's going to give you what you are looking for. So this is the back end as well, and we have the S plus or Z, which is conjugate gate of what? Z gate phase. Likewise, this is the difference. We have what? SDG. That's what we use. Why other is X, Y, Z? This one is holding its own with SDG. Please have this at the back of your mind. This SDG, you can use phase what? One of the gates. You can have. We are still going to talk about gate and so on. So these are the gates. We have the C3 gate. The C3 gate have P. So this. And this is the matrix, and if you want to run, just write Q is equal to what? Quantum socket open bracket Q, which the Q is representing what? Your quantum register. And also we have QC.E, which is representing the gate we are using. This gate C is the gate you are working on. So likewise we have the other gate and we run. So this is the output, and run the back end result as well. So that's what's going to give to us. So other gates that we have, we talk of these are the single gates we have, and this. So running through all the gates, we have the U gate, we have the P gate, we have the amplifying gate, we have the poly gate, and under the poly gate we have the S flipping gate, we have the Y flipping gate, Z phase gate, and Adamon gate, and we have the S and Z root Z gate phase gate, and we have the conditional gate, conjugate gate, we have the Z3 gate, and this Z3 gate have the T gate. So those are the single gates that we have, single quantum operators, single qubit quantum gates that we have. So that's it. Thank you.